to all and welcome to this lecture. We are in module 11, lecture number 1, Intrinsic Charges in Quasi-Static Operation part 2. In this lecture, we will see how these charges under quasi-static operation can be defined in weak inversion, all region model and depletion and accumulation. We will see how these charges are distributed in the channel, let's say for weak inversion. These are the learning outcomes of this lecture, which helps you to understand the behavior of charges in weak inversion when you are doing quasi-static operation. Let's see what we have done in last lecture. We related the charge which is either QB or QI or QG in terms of terminal voltages. We said that we do not have any closed form equation for strong inversion where charge is related with position, and hence we change the variable by rewriting the equation for drift current, because drift is dominant in strong inversion, which is nothing but W into mu into minus Qi dash into dVCB divided by dx. In general, this is what d psi x divided by or d psi s divided by dx, but we know when you are in strong inversion, psi s is nothing but phi naught plus VCB, or d psi s is equals to dVCB. That's what we have already done when we were discussing about strong inversion in our DC case. So we change the variable and then we put back those changed variable in final expression to calculate the inversion, bulk and gate charge, meaning we did that W into L 0 to L into Qi dash dx can be rewritten as W into minus into mu W divided by IDSN with a changed variable as dVCB. In that, we said that the limit of this integral will be VSB to VDB. To solve the fictitious charges, for example QD, we required X, and also we showed how we can relate the X in the sense the position with respect to voltage. Then we said that we can relate all these charge expression in a simple form in terms of eta, where eta is nothing but 1 minus VDS divided by VDS dash, where VDS dash is nothing but VGS minus VT divided by alpha. So in general, we got a closed form equation for inversion charge, bulk charge, QD, QS and QG, and we plotted those charges with respect to VDS for two cases, one when VDS is equals to 0 and one when VDS is equals to VDS dash. In this case, eta is equals to 1, and in this case eta will be equals to 0. For that, this will give me an idea how the charges are distributed in the channel, especially how the fictitious charges, that is QD and QS, are distributed in the channel, which says that if you take eta is equals to 1 or VDS is equals to 0, it is exactly half of the charge which is of channel charge. It means, or inversion charge. Inversion charge was given by this point. Exactly half of that point is nothing but what? QD and QS is exactly half of QI divided by 2 when VDS is equals to 0, because your channel is uniform in that condition, right? However, when you increase VDS, ultimately the charges at the drain side will reduce. That is what your QD graph will reduce and QS will be higher, that they compensate the rate of change of charge in the channel to show you the final QI in terms of the available voltage, which is nothing but 2 by 3 into W into L into COX into VGS minus VT in strong inversion when your VDS is greater than or equal to VDS dash. So now let's see how these charges are distributed in weak inversion. So we'll just review our weak inversion theory. We said that in weak inversion, the inversion charge is very small to QB, and we developed that QB is nothing but minus of gamma into COX into square root of psi s, where if you divide by per unit area, ultimately it will give you QB, which is nothing but minus gamma COX square root of psi s. But you remember that in weak inversion psi s is replaced by psi sa. If you plot surface potential with respect to VGB, the graph was like this, and we said that this shows the weak inversion, which is similar for depletion case where psi s is equals to phi f, correct? So accordingly, we can simply rewrite the equation QB as W into L into COX dash into gamma times of this equation, which simply says my bulk charge will not change along the position. If you have source here, drain here, so the bulk charge will not change. That is what we have discussed in weak inversion. The surface potential at both ends will be almost same, correct? Now we can simply find out the gate charge by the charge balance equation, which says that QG dash is nothing but minus of QB dash, or if you are writing in terms of total charge, you can simply rewrite as minus of QB plus QI minus of Q naught, where Q naught is oxide charge, and for weak inversion we can consider QI is very small than QB, so you can get the final equation as, so QG is equals to minus QB minus Q naught. Now let's see how can we find out the inversion charge, though the inversion charge is less, but it is there in weak inversion. So we need to find out the inversion charge along the position x. So this is 0, this is L, and this is the direction x. This side you are having source, and this side you are having drain. This region is channel. If you remember, we have plotted this graph and shows that the inversion charge varies linearly in weak inversion. We showed this graph like this, and accordingly we defined the diffusion current, which is dominant in weak inversion. So this will be QIL dash, and this will be QI0 dash. We define the current, which is nothing but IDS2, or in weak inversion we can simply write IDS is equals to W divided by L into mu into phi t into QIL dash minus QI0 dash, meaning my charge in weak inversion varies linearly. So QI is function of x in weak inversion, and hence we can simply rewrite this line equation as QI dash x is nothing but QI0 dash plus x divided by L into QIL dash minus QI0 dash. You can do a quick check. If you put x is equals to L, means at the drain side, ultimately at x is equals to L, you will get what? QI0 dash plus QIL dash minus QI0 dash. So you will get QIL dash at the drain side, right? So this shows that your inversion charge linearly varies. Now I can use the same formula what I was using in the previous lecture for QI. Now here the advantage is that I do have a charge which is dependent on x, and I do have a simple formula which can be given as QI0 dash plus x divided by L into QIL dash minus QI0 dash, right? This is nothing but QI x dash. So I'll put that in this formula, 0 to L charge per unit area into dx, 0 to L. Now this expression can be put here, QI0 dash plus x by L into QIL dash minus QI0 dash, and you need to do integration along with x. So when you do the integration of first term, it will give you QI0 dash into L. I am just putting the limits directly because the integration of 1 will be x, and you put limit 0 to L, so L plus 1 over L. The integration of x will be x square by 2. So you will get 2, and if you put x square will be L qi L dash minus qi 0 dash, right? This L and L get cancelled and you will get W into 2 qi dash qi 0 dash plus qi L dash minus qi 0 dash divided by 2, which will give you this final formula, which means the inversion charge is just the average of inversion charge at source side and drain side will give you the total inversion charge in the weak inversion. Similarly, by using the same approach, you can calculate QD. You remember, to calculate QD, we said that W into integration of 0 to L into x by L into qi dash dx. Now, when you rewrite this equation, 0 to L, x by L, qi dash can be replaced as qi 0 dash plus x by L into qi dash L minus qi 0 dash. When you do this integration, put the proper limit. Once you will get a square term and one you will get the simple integration. Then when you solve this, you will get this expression. So ultimately, this shows that how my fictitious charge QD varies in the channel. Here, interestingly, you can see the QS and QI. If you sum up, you will get what? The same QI, right? So these charges in weak inversion can be easily calculated because the inversion charge depends on the position. Now, in general, what happens in weak inversion, if you have the depletion region like that, right? Now, in weak inversion, suppose you are changing VSB, or let us consider a quasi-static analysis. So, if you change Vs or if you change Vb, right, then because of change in this, the depletion region charges changes, because change in VSB creates a change in VSB, because the change in VSB creates a change in depletion charge, and the change in this depletion charge is significant as compared to the change in these fictitious charges QD and QS. That is what, in general, we ignore these charges, that is QI, QD and QS, in terms of quasi-static analysis also. Now let's see how can we define an all reason model. We have seen separately in strong inversion and separately in weak inversion, but the question is, can we relate these two and form a all reason model and to calculate the inversion charge? So yes, we will use the general expression of inversion charge, which is nothing but minus COX dash into VGB minus V flat band voltage minus IS minus QB dash, where I am putting the QB dash as this, and you will get this expression. This expression many a times we have used in our previous analysis. So what needs to be done is, so you need to be considered the current which is dominant by drift and diffusion both. Here we are considering the all reason model means the total current, that is mu into W into minus Qi dash into d psi s by dx plus W into phi t into dqi dash divided by dx. This is the expression for the current. This is drift component and this is diffusion component. So we need to use both the equations because we are solving for all reason, not separately for strong or weak inversion. Now here again we need to do the same exercise because we do not know how the charge varies with x. So what we'll do, we'll change the variable. So we can simply change the variable as minus mu into W into Qi dash d psi s divided by I ds plus W into phi t, here mu term will come, mu divided by I ds into dqi dash. Now what I will do, I will put this variable dx in again the same equation. Qi is equals to W into integration 0 to L Qi dash into dx. When you put this integration, you will get a term which is having constant mu w square divided by IDS into integration of inversion charge square, because one Qi is here, one Q is here, and the integration with respect to surface potential. So you need to choose the limit accordingly. Now the limit will be what? Psi S0 to psi SL. The second term will give you plus mu into w square into phi t divided by IDS integration of Qi0 to Qil dq dash into Qi dash. When you solve this integral, ultimately you will get the closed form equation of Qi for all region of model. Now, I am not doing the complete calculation, but I will give you some glimpse that second term you can simply find out as mu into w square into phi t divided by IDS, and if you do the integration of this, you will get Qi dash square L or minus Qi dash 0 square divided by 2. Okay, so I am not solving the first term. For the first term solution, you need to put this Qi in terms of surface potential, which I just showed you, that in terms of surface potential you need to rewrite the Qi dash, put it here and solve the integration, which is, yes, it is complex because there is a square root term. So you need to solve to get the complete closed form equation. Now let's see. So we are getting now, when you solve the second term, ultimately you are getting this term in the right hand side. Now let's do a quick check for this model. Consider for weak inversion. Consider weak inversion, right? If it is weak inversion, the right hand side or the first term will be negligible. In the right hand side or in the second term, w square mu into phi t divided by 2 times of IDS into Qil dash square minus Qi0 dash square term is there. Now let's put IDS value for weak inversion. So this will give you w square mu into phi t divided by 2. Now IDS for the weak inversion we have already derived as w divided by L into mu into phi t, right, and into Qil dash minus Qi0 dash. And in the numerator you can just split it as a square minus b square as a plus b into a minus b. So ultimately you will get Ql dash plus Qi0 dash into Qil dash minus Qi0 dash. This term will be get cancelled, phi t, mu 1 w get cancelled, and ultimately you will ended up with w into L into Qil dash plus Qi0 dash divided by 2. That was a simple expression we calculated here. We said that the inversion charge is nothing but just half of Qi0 plus Qil divided half of the sum of Qi0 Qi dash. So here Qi is nothing but w into L into Qi dash 0 plus Qi dash L divided by 2. So we can simply say our all region model holds good. Now can I simplify this model with some linearization? We have already done when we were discussing about the simplified strong inversion or weak inversion models. For that, this integral we can simplify it. How? We can simply linearize the inversion charge. You remember we said that inversion charge can be linearized as alpha into Cox dash into psi. So dqi dash is can be written as alpha into Cox dash into d psi s. So to get the changed variable of this integration, right, I can put this d psi s as dqi dash divided by alpha into psiox, right. By doing this linearization, we got the current expression as this, which is nothing but w by L into mu into minus 1 over 2 alpha Cox dash into Qil square minus Q0 dash square. This is the drift component, and this was the diffusion component. Now to solve for a complete Qi, what I can do, I can simply rewrite this expression again with minus mu w square divided by I ds integration minus of Qi dash, so plus of Qi dash, I have taken minus out. Instead of d psi, I can rewrite as dq dash, and I need to divide by this alpha into cox term. Now the integration limit will be in terms of q dash, which is Qi dash 0 and Qi dash L. This is the part which will given by delta psi s, but there was an additional Qi which was there in the integration, and hence ultimately you need to solve mu into w square divided by I ds into integration of Qi 0 dash, Qi L dash and Qi dash square dq dash divided by alpha into cox dash. Now here, as you are doing the integration of a square term, you will definitely get a power 3 term, so which is similar as q to the power 3 Qi dash minus Qi 0 dash to the power 3. I am not doing a complete calculation here. You can simply solve the integration. When you solve the integration, you will get a power 3 term here, and in the denominator, when you replace this current IDS by this, you will have a square power term, which is Qi 0 square minus Qi L square term. Now you can simply replace this power 3 term as a cube minus b cube can be written as a minus b into a square plus b square plus ab. Now you can simply relate what I am saying with the final expression. The final expression will come out like this, where a is Qi dash 0 and b is Qi dash L. So you can simply rewrite as Qi dash L square plus Qi dash 0 square plus AB, so Qi dash L into Qi dash 0. So this is from the numerator, because of this term will come when you solve integration, and this term is due to diffusion part, that is the second part of this integral what we have already solved, and in the denominator you will get a square minus b square, which can be written as a minus b into a plus b. So from the numerator and denominator you will get this word common, and in the denominator you will get a plus b, that is what Qi L plus Qi dash 0 term is coming. So we can simply say this model is a simplified all reason model, which can help me to solve the integration easily, because I need not to go for a complete calculation in terms of surface potential. I simply linearized my inversion charge model in terms of alpha cox dash into psi s. Right? Now let's do a quick check for, let's say, strong inversion. In this case, if I consider the strong inversion, then Qi L dash will be 0. Let's say we are considering for strong inversion and saturation, right? Then Qi L dash will go 0, because near the saturation the inversion charge will approach to 0 because of pinch off. Here you are left with W into L into 2 by 3. This term will also 0 because Qi L 0. You will get Qi 0 dash square. This term is due to diffusion. So we are considering the strong inversion saturation. This will be 0. Similarly, this term is coming because of diffusion, right? So this will be ignored, and this term will go 0 because we are considering for strong inversion saturation. So in the denominator you will get Qi dash 0. This will get cancelled, and ultimately you will get the total charge as W divided by 3 into L into 2 into Qi dash 0. That is what we have derived of the inversion charge in saturation region strong inversion, right? Now when you operate this device under quasi-static operation, let's say for digital application, then you turn on the device and turn off the device. In general, turning off the device is relatable with depletion and accumulation region, and hence you need to define these charges in depletion and accumulation region also. In general, in depletion and accumulation, the inversion charge is negligible. So I can simply consider Qi is equals to 0, and I can again rewrite the potential balance equation to find out what is the gate charge and what is the bulk charge. So that is what we are rewriting these equations again, which shows that the oxide charge is nothing but VGB minus psi s minus phi ms. You remember, this is a basic potential balance equation we have written for two terminal structure, which is VGB is equals to psi ox plus psi s plus phi ms, where phi ms is the contact potential and psi ox is an oxide potential, psi s is the surface potential, out of which we can rewrite for psi ox, and you remember the gate charge per unit area can be given as COx dash into this psi ox. Now, as we are interested in the total gate charge, we need to multiply with W into L. That is what you are getting here, right? And again you solve for charge balance equation. Total charge balance equation was QC dash plus QG dash plus Q naught dash is equals to 0, where QC in depletion is dominant by QB, and in accumulation it is dominant by whole charge, which is positive. So for the total charges, I can again rewrite as QC plus QG plus Q naught is equals to 0 by multiplying the overall area of the gate, right? Now, in deep in depletion, what happens? I can use the same approximation, considering the inversion charge will be 0, and the gate charge can be simply calculated as minus QB minus Q naught. In deep in accumulation, psi s varies little with VGB, so we can get the value of the charge accordingly. Now, let's see how these charges, which we have derived for quasi-static analysis, that is Qi, QB, QG, or let's say Q naught, how these charges varies with the voltage, because these charges are available in the MOSFET, and ultimately you are tuning or changing the gate voltage. In previous lecture, we have seen that how the charges varies with VDS. You remember, we said that if you increase VDS, the gate charge was showing this trend, the bulk charge was showing this trend, and the inversion charge was showing this trend. And we argued that how the fictitious QD and QS settled themselves so that you will get the reduction in the inversion charge in the channel. Now let's see what will happen if you increase VGS. So we just plotted an ID-VD characteristic, and now I am increasing VGS. So these lines shows the increase in VGS. Let's say this is, let's say VGS1, VGS2, VGS3, and so on. Let's say VGS some 8 or so, right? This is an increasing trend of VGS, correct? So VGS 8 is greater than VGS 1. Now the moment of the operation principle, now the transistor will move with varying VG from VG1 to VGS from in the following reasons. That is, first, when VGS is very small or negative, it will be in accumulation, then it will enter into depletion, then it will enter into weak inversion, then it will goes to saturation, strong inversion, and after that, when VGS is very high, it will enter into strong inversion, non-saturation region. Because we have already defined this kind of saturation non-saturation boundary as VDS should be less than equals to VGS minus VT by alpha, which will give me the non-saturation region, right? So if you see here, to keep the operation in non-saturation region, VGS should be greater than equals to alpha times of VDS plus VT. So here this dotted or the arrows shows the movement of the MOSFET from different reason of operation, that is accumulation, depletion, weak inversion, moderate inversion, and strong inversion. In strong inversion, you will first achieve the saturation region, and then when you increase VGS, you will enter into non-saturation region, which is clearly from this graph as well. This is a saturation region. The current is saturated, right? Here the current is saturated. But after this point, what happens? The current is linear. So you are entering into the linear region. Now, let's see how these charges will look like with these terminal voltages. So we are keeping VDS fixed and we are just sweeping VGS. And we are plotting different charges. Here gate charge, bulk charge, here inversion charge, and how these fictitious charges, that is QD and QS, supports the inversion charge. So let's get started with understanding the increase in VGS from flat band voltage. So if you see, if VGS is equals to flat band voltage, then at that moment the channel charge will be 0. That's what we have already discussed, because the flat band voltage is a voltage which makes the channel charge 0, right? So there is no charge present at that. Now when you increase VGS, what will happen? The gate charge will be positive, right? And accordingly the channel charge will be negative. This region of operation is depletion and this region of operation is weak inversion. So ultimately this 2 points shows the weak and depletion region of operation. Now when you increase VGS, the depletion charge or bulk charge continuously increases, but at a certain point it will become constant. That is what we have discussed. In non-saturation region of operation, almost uniform depletion region will form, right? That is what the depletion region charge goes and becomes constant when you enter into non-saturation region by increasing VGS. Now how gate charge look like? Again, the bulk charge was a result of the gate charge. So when you increase VGS, meaning you are increasing more charges on the gate, that is what it becomes positive, positive, and like this. Before flat band voltage, the gate charge will be negative. Correspondingly, there will be an accumulation region and hence the channel charge will be positive. More interesting case is to see how QD and QS varies under this operation. So when you increase VGS beyond a point that we generally called as threshold voltage, beyond the point my current gets started. This is a saturation region, right? So remember, it is a square law dependent, that is VGS minus VT whole square. Considering that, we are not considering, assuming that we are not considering short channel effects, velocity saturation, mobility effects, etc. So this is just a quadratic part, and after that it becomes linear, because you know the equation is nothing but what? Mu into W divided by L into COX dash into VGS minus VT into VDS minus alpha into VDS square divided by 2. So that is what a slight change is visible, because you are entering from a quadratic part to a linear part. Similarly, QD and QS will follow, because we have also seen that how QD and QS are relatable with QI. So as you are entering in saturation region, the QD will be smaller and QS will be more. We have discussed that point, that when you increase the voltage, drain voltage, then the channel charge near the drain will be lesser, and hence they will adjust itself to give rise to the change in QI. Finally, after this all calculation, we found a relationship between Q and V. You remember, in previous lecture, we discussed that our main goal is to find out the terminal current, and we said that the terminal current can be calculated by chain rule as delta Q of, let's say, gate divided by delta Vg into delta Vg divided by delta T. You can take this for any terminal. Maybe if you want a drain change in the inversion charge, you can say delta Qi divided by delta Vd, or let's say Vg into delta Vg divided by delta T. We have seen that chain rule in previous lecture, and we have completed our job to form a relation between Q and V. Now this is nothing but how the voltage is changing with time, right? And if we multiply, then we can form a closed loop form of terminal current equation under quasi-static operation. So let me summarize that in this lecture we have discussed about weak inversion, depletion and accumulation region when different charges are dominated under quasi-static operation. We said that in weak inversion, as Qi dependent on x, we can simply do the integration by putting Qi, which is a function of x, as Qi 0 dash plus x by L into Qi L dash minus Qi 0 dash. Further, we have derived the equations for all region model by changing the variable of dx in terms of d psi s plus dq, where this was a bit complex integration because to change the variable of d psi, again we need to change the variable in terms of dq as qi dash is equals to minus cox dash into vgb minus v flat band voltage minus psi s minus gamma root psi s. To avoid this complexity, we said that we can go for a simplified all region model. In that, we just linearize the inversion charge as alpha into cox dash into psi s. So we change the variable of d psi s by dq dash alpha into, and at last we said that how these charges vary with gate to source voltage. We found that when you increase the gate to source voltage, ultimately the region of operation of the MOSFET entered from accumulation to depletion to weak inversion, then moderate inversion, then strong inversion saturation, and then strong inversion non-saturation. So we will stop here for today. Until then, take care.